The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All right, so today we're going to wrap up the chapter with section 8.9. Tonight's homework is section 8.9 in the chapter review. Tomorrow we'll review for the test, which will be on Monday. So on Monday, there'll be no regular class meeting. You'll just take your test. You can always take it early. It's due Monday night at 11:59 p.m. But once you open it, the time starts. Okay, well, having said all that, let's go ahead and take a look at section 8.9 for today. And we're going to deal with what is called variation. We're going to look at three kinds of variation today. The first kind is called direct variation. And a general form for it is y equals kx. K is known as the variation constant, or the constant of variation, or the constant of proportionality. I'm just going to call it K is the variation constant. So what is going to happen with direct variation? We're going to be given information that will allow us to determine what K is for a particular instance. We will then put that value in place of K and go on to a follow-up question. With direct variation, if X increases, so does Y. If X decreases, so does Y. So X and Y go up and down together. Let's take a look at an example of direct variation. All right. This problem says the following. It says free fall. An object in free fall travels a distance s that varies directly to the square of the time t. If an object falls 1,024 feet in 8 seconds, how far will it fall in 10 seconds? All right, so we've got an object in free fall that travels a distance s. So distance s that varies directly to the square of time t. So time is t, and so what we get is s equals kt squared. The distance varies directly as the square of the time. Now, k, or the variation constant, wasn't even mentioned in the description, and quite often it's not mentioned, but it's always contained in all the variation formulas. So from the reading, we've got this, okay? Then it says, if an object falls 1,024 feet in 8 seconds, so by putting 1,024 in for the distance and 8 seconds for the time, we get this situation, which then becomes that, because 8 squared is 64. We can then come back and divide both sides by 64, and we get, let's see here, 1,024 divided by 64 is 16. So now we know that K is 16. So that's going to go up here. So now we have this. So we read the problem, we write the formula according to the problem and the variables they mention, if they do. We then plug in the numbers to solve for K. We then put the number in for K and go on to the follow-up question. It says, how far will it fall in 10 seconds? So S equals 16 times the time squared, which is 16 times 100, which is 1,600. And that is feet. So how far, I can't even talk. How far will the object fall in 10 seconds, 1,600 feet. So this again is an example of direct variation. As the time increases, so does the distance that it falls. Any questions about this one, Antonia?
No, thank you.
All right. Second example of variation is called inverse variation. And that looks like this. You have a reciprocal situation. It still contains the variation constant, but the way this works is that if x increases, y decreases. If x decreases, y increases. So they vary inversely. Do you ever go to a coffee shop and purchase a coffee or a latte or something?
I do teas.
You do tea. So do you ever get them at a shop?
Yes.
What do you pay for them?
Sometimes it depends. If you want fruit, it's like $6.
Okay, so how often a week do you go and purchase one for $6?
Maybe two times a week.
Okay.
Monday and Fridays.
Okay. So 2 times a week for $6. If the price was $10, would you still go and get any?
No.
What if it was $8? Would you get one?
No, I got two. No, I got two because it's kind of price is just a tea, just because they add fruit.
Okay. What if it was cheaper? What if it was $3? Would you go more than twice a week?
Yes.
Okay. So like how many times?
Like maybe every day, because that I get that
Sure.
I get with the $3 I would get two per, how right now I'm paying.
Sure. I get it. My point is this. What we have here is a situation where as the cost goes down, the amount that you're willing to purchase goes up. Do you see that?
Yes.
As the cost goes up, the amount you're willing to purchase goes down. So there's that inverse variation.
Yes.
Okay, that's all I wanted to establish, was just that idea. All right, so let's take a look at an example. Let's see here. It says the frequency of vibration of air in an organ pipe it varies inversely to the length of the pipe. So we've got the frequency of vibration, and let's use an italicized F for that, and the length of an organ pipe, let's call that L. Okay, so F is going to stand for the frequency of vibration. L is going to stand for the length of the organ pipe. The frequency of vibration of air in an organ pipe, so that's F, varies inversely as the length of the pipe. Again, K wasn't mentioned, but K is in the formula and K is always on top. So from that sentence, I get this formula. Are you okay with how I got it?
Yes.
All right. Now a follow-up information to determine what K is. If a pipe 2 feet long, so that's the length, vibrates 256 times. So from that, we can determine K. We're going to multiply both sides of this formula by K. So K equals 512. All right, 2 times 256. So we're going to take that and put it into our general formula to get a specific formula, which is that. All right. So far, so good?
Yes.
It says, how many times per second will a 6-foot pipe vibrate? So the length is 6 feet. If we take 512 divided by 6, we get 85.3 repeating, which would be 85 1/3, let's see, times. So again, reading the story, we determined it was inverse variation. Frequency varied inversely with the length of the organ pipe. So we got this. We were given some information that allowed us to determine K. We put the value of K in, and then we used some follow-up information to answer the final question. All right with that?
Yes.
Okay, so we've had direct variation and inverse variation. We have one more example of variation, and that's called joint variation. Have you ever had a joint checking account?
Yes, I do have one
So what does that mean, that it's a joint checking account?
that's combined with the other person.
Right, there's more than one person on it. Okay, so joint variation, a general form of that looks like this: y equals k x z. So again, k is present in the variation formula, but there's more than one variable on the right side of the equation. So y equals k times at least two different variables. All right, so that's joint variation, where you have more than one variable on the right side. Okay, let's see here. Oil storage. The number of gallons of oil that can be stored in a cylindrical tank varies jointly as the height of the tank and the square of the radius of its base. The variation constant is 23.5. Find the number of gallons that can be stored in the cylindrical tank shown. Okay, so let me draw a picture of the tank. And they tell us that it's 15 feet across and 20 feet high. Okay, so there's this oil tank. Now, the number of gallons of oil that can be stored varies. Okay, so number of gallons of oil, let's call that, how about G, capital G for gallons, varies jointly as the height of the tank. So height of tank we'll call H, and the square of the radius, and the radius we'll call R. So G stands for the number of gallons of oil that the tank can hold. H stands for the height of the tank, and R stands for the radius. All right. Now, K, the variation constant, they told us it was 23.5. So sometimes they don't even mention it. Sometimes they mention it and in fact give you its actual value. But let's write the formula. All right. The number of gallons, so that's G, varies jointly. So we've got K as the height times H and the square of the radius, R squared. So G equals KH R squared. Sorry. So far, so good?
Yes.
All right. Now, we know that K is 23.5 because it was given. H, the height, is 20 feet. Careful, the radius is not 15 feet. That's the diameter. What's the radius of a circle? It's half the diameter, right? So that would be what, 7.5 feet? You okay with that?
Yes.
But that's supposed to be squared. Don't forget the square. So let's see here. If I take 23.5 times 20 times 7.5 squared, I get 26437.5, and that's gallons. So this particular oil tank could hold 26,437.5 gallons. So that's a example of joint variation. You all right with that?
Yes.
Right, now we're going to do some translating, and that is I'm going to read a statement in words, and then we'll translate it into symbols, and then we'll go the other direction. So let's say, for instance, we have this. A varies directly as the square of P. So A equals KP squared. You all right with that?
Yes.
Z varies inversely as the cube of T. So Z equals K over T cubed. All right with that?
And you said does Z what? Z varies?
Z varies inversely
Uh-huh.
as the cube of T.
Okay.
Can you see the whiteboard screen? Can you?
Yes, I can now.
Okay.
My phone was just, my internet is kind of low.
Okay, you're trying to do this on your phone. Yeah,
Yes.
that makes it tough. Okay. We good to go on?
Yes.
All right. C varies jointly as X, Y, and Z. So C equals K, X, Y, Z. Again, variation constant is included. All right with that?
Yes.
All right, let's see here. M varies inversely as the cube of N and jointly as, as X and the square of Z. So we've got two different variations going on in the same problem. M varies inversely as the cube of N. K goes on top, and jointly as X and the square of Z. So M equals K times X times Z squared all over N cubed. So do you see how we've got more than one type of variation in that single problem?
Okay, that's how you got that into the third?
Right, because inversely as the cube of N, so that's going to be down below, N cubed.
Yes.
Jointly as X and the square of Z.
Okay.
And K, of course, is always on top. All right.
Okay.
All right, now R equals KT. Translating that into words, you would say R varies directly as T. So we're going the other direction now, taking the formula, writing it in words. All right.
Yes.
B equals K over H. We would say B varies inversely as H. All right with that?
Yes.
Okay. Let's see. U equals K R S squared T. We'd say U varies jointly as R, the square of S and T. Questions there?
No.
All right. Let's see. R equals KL over D squared. So we'd say R varies directly as L and inversely as D squared. All right with that?
Yes.
So you've got three types of variation. You've got direct variation, y equals kx. They go up together, they go down together. You've got, let's see, inverse variation. If one increases, the other decreases. If one decreases, the other increases. And let's see, joint variation, where you've got more than one type of variable on the right side of the equation. Each one of these has K. K is always on top. Sometimes it's mentioned, sometimes it's not. All right, well, that's all I've got for you. So this is 8.9 variation. I'll be back at 1:15 this afternoon with an office hour. I'll be back tomorrow morning at 11:30 to review, getting ready for your, chapter 8 test on Monday. So I'm going to go ahead and stop the recording.